So we're excited to have Chris Harrison here today. Chris is a PhD candidate at CMU at the HCI Institute. His research is in the area of building new interaction techniques for mobile devices and other computing platforms by building creative sensing platforms and software for those systems. In addition to having a very productive graduate career and many Best Paper awards, Chris is also a TR35 awardee and also a Forbes 30 under 30 recipient. So a lot of accolades for his work. And so I'll let Chris take it over from here. Thanks.
Yeah, thanks, Reddick. So thank you all for coming today. I'm really thrilled to be here. So I hope that everyone in this room can appreciate just how amazing mobile devices are. These are really kind of incredible and sophisticated computers that can do a whole host of things. Send emails, take photos, make reservations, get directions. You know, it's an incredible, incredible transformation from their humble beginnings. And indeed, they're really likely to become the chief conduits for many type of information retrieval tasks, certainly for content creation, and certainly also for communication. And this is really the product of a very long evolution. And instead of starting like this, they actually started with devices more like this. So this is the SCR300. It was really the first mass-produced portable two-way communication device on the planet. And it's what GIs in World War II nicknamed a walkie-talkie, because at the time, the fact that you could walk and talk without a 500-foot spool of wire coming out of your backpack was actually a really kind of remarkable feat of engineering. And so to give you kind of some perspective here, this weighed 35 pounds. You wore it on your back. Like a modern device, it came with lots of awesome ways to accessorize, which added about 10 pounds. And you could talk to someone, assuming that they were no more than 3 miles away. So now if we jump 40 years into the future, into the 80s, we have the first publicly available cellular telephone, the Dynatac, made by Motorola. And it was still pretty hefty at 2 pounds. And really more importantly is that it cost $4,000. That really put it out of the reach of a lot of people. But nonetheless, it constituted a really significant advance and opened up new capabilities to people. Now if you jump ahead just a mere 25 years, kind of half the last interval, we land into the kind of modern era of smart touchscreen devices. And this is the first generation iPod Touch, which just celebrated its 5th birthday last semester. And on its release, it cost under $300. It weighed about 1/5 of a pound, and it could do things that desktop computers couldn't do even 10 years before it. So it's a really astonishing progression, and it's been made possible because there's been tremendous advances in computing technology. So things like CPU power, memory, and storage have increased essentially exponentially according to Moore's law. And then there's a whole slew of other computing factors that aren't quite exponential, but nonetheless kind of always march forward. And that's things like bandwidth and screen resolution, viewing angle, camera megapixels, and the list goes on. And what's happened is these have culminated in incredibly cheap, powerful, and energy-efficient computers that happen to fit into our pockets, right? And it's really quite an amazing feat. And in many respects, these are supercomputers today. They would have loved one of these devices back in the 70s to do fluid simulations. These are multi-core, have hardware acceleration for things like graphics, have gigs of memory and so on, right? But we certainly don't use them like supercomputers, and we don't even really use them like desktop computers. And there's some interesting reasons about kind of why they're being held back. So, why don't we have devices like this, right? We could actually build this. We have the technology, but we haven't pursued it. And why is pretty straightforward. So if we look at human factors instead of computing factors, we can see that our fingers haven't become pointy styluses for input. Our vision hasn't improved to read it. We can make a postage stamp-sized screen, but we just wouldn't be able to read it effectively. And our dexterity hasn't improved to handle tiny buttons and so on, right? And the list goes on. And so what happens is if you look at kind of the evolution of mobile devices, we see something kind of rather remarkable, and that is that it's really kind of bottoming out. We can't get a whole lot smaller without devices getting totally unusable. And this is really a lower bound that's set primarily by us, by human factors. So we really just can't get a whole lot smaller. And this is really quite a momentous moment in the history of computing. Often today, the biggest and slowest part of a computing platform is the human, right? So one of the kind of fundamental issues with mobile computing is that our fingers are relatively big and they're not likely to shrink anytime soon. And if you're going to have a screen that's going to fit into a pocket, it means that the interaction area is going to be kind of inherently small. There's a contention there, and that's very hard to escape. Now, there's a second fundamental problem, which is a little bit more subtle, and you have to think about a musical instrument like a guitar. This, too, is a multi-touch device. It's a much older multi-touch device, but it is one nonetheless. But it sounds a lot better than its counterpart in the App Store. right? And why is actually pretty apparent to anyone who's played an instrument. There's a lot of dimensions to touch that we're simply throwing out on a touchscreen. Things like pressure and shear and twist, contact area, and so on. And if you really think about the number of ways that your hands can manipulate the world, it's actually pretty mind-blowing. You know, our hands and fingers are incredible. But what do we do with computers? Well, we mostly kind of poke at them like this, right? It's a lot of, maybe we poke at them with 2 fingers, but it's really a lot of poking. And that's a very simplistic way to think about touch interaction. And what I like to kind of, talk to students at CMU about is, imagine if all we could do in the world was poke at it. You have to poke your shoes on, poke those shoelaces together, poke your car to work, poke coffee in your mouth. All these things would be ridiculously difficult, The world around us would be unusable. But for whatever reason, we think this is sort of the pinnacle of input for touchscreens, and clearly that's very wrong. So kind of a fundamental problem number 2 is that input on today's devices isn't very rich. So not only is there very limited space to operate in, but then on top of that, we don't even really make the most use of that small space. And so it's really these 2 problems that I've spent a lot of time at CMU thinking about. And unfortunately, I can't go through every project here. Instead, I'll be focusing on kind of one thread of research. Now, it's important for me to note that my research really heavily relies on rapid prototyping and rapid ideation, right? So instead of just sharing 1 or 2 projects with you, I'm going to be sharing a progression of projects with you so you can see kind of the ideation process and how, the kind of methodologies that I employ in my research. So first, to kind of give you some context here, I need to talk about the root objective of my research, and that is to amplify human abilities. And that's really the nature of any good tool, and certainly computing is one of the most powerful tools that humans have ever devised. So how do we amplify human ability? Well, the problem with our set of inputs and outputs, human sets of inputs and outputs, is that it's mostly fixed, which is what I alluded to a few minutes ago. But the kind of user I/O of a computing system is dynamic. We can innovate and enhance it. And by doing so, we can enhance human I/O. And what I'll be talking about today are projects that attempt to do just that. And ultimately, it's what inspired my dissertation work. So first, I want to start talking about one of those 2 problems that I brought up in the beginning, and that is how do we increase interaction richness? And so to give you just a little bit of a flavor for this domain, I'm going to show you one project, which is TapSense. Now, as I mentioned earlier, touchscreen interaction is really a lot about poking today, but we know that our fingers can do a lot more. So for example, one of the ways we use our fingers in the real world is by using different parts of our fingers, and touchscreens don't do this now. And so what we built in TapSense is a touchscreen that can actually take advantage of the different parts of your fingers, and it does this acoustically. So when you tap with the pad of your finger, kind of the soft pad here, or the bony knuckle or the hard keratin of your fingernail, those all sound different. And so with a little bit of acoustic modeling and machine learning, we can actually build a touchscreen that actually has different types of touch. Now, one kind of very simplistic use for this is enabling something like a right click. So if I click on a photo like usual, it opens up, but I can also knuckle tap to have a contextual menu appear. And we know this has been a very successful paradigm in desktop computing. So really, instead of just getting an XY coordinate, we're getting XY and also a type. So it's an extra dimension. It's not that the device is any bigger, it's just better. So this is actually quite a significant thread of research with a bunch of projects. But today I'm actually going to be talking about the other strategy I've pursued, which is increasing the interaction area. Now the big catch here, it'd be great to just have a bigger device. Now we'd say, well, the problem with this is that the screen's too small, so why don't we put a 10-inch screen on it? Well, then clearly it's no longer a mobile phone. So you have to somehow increase the area without actually making it bigger, and that's a bit of a catch. And so to explore this, I've looked at 3 different sub-strategies. And today I'm going to focus on just the last one here, which is appropriating surface area. So, this is a scene that should be, fairly familiar to people. You have a mobile device sitting on a table. It's probably, here a bunch of times. It's certainly true right in front of me. So wouldn't it be great if we could temporarily steal all that surface area for interactive use? That would allow us to kind of escape the small confines of the device and instead use the environment, which has plenty of surface area. But obviously, the kind of core challenge here is technical. It's a really cool idea, but how do we do it? So one of the first projects that I did in this area was called Scratch Input, and it's, I think, a really nice example of how you might do this practically. And the core idea here is to let the devices, which are sitting on the table, to act like contact microphones. So gravity is already acoustically coupling these devices to tables. And when it's situated like this, it can actually hear the acoustics inside of that surface, such that when you use your finger, when you drag your fingernail over the surface or you tap on the table, the acoustics propagate through the medium of the table, and the microphone in the device can pick that up. And so you can, for example, write an S on this tabletop, and I can put my phone into silent, or V for voicemail, and so on. And what's really nice about this is that when you're done, you can just pick up your device and go. There's no permanent instrumentation of the table. So this notion of kind of appropriating surface area from the environment really resonated with me. So foremost, that we can have a device that remains small, but allows you to have large interaction area. And this is not only more comfortable, but also more accurate for human input. We also get tactile feedback, which is really important. So by operating on physical surfaces, we get tactile feedback as opposed to kind of clicking in the air. And if we have projectors, we have the ability to also project information onto the environment, so we have coordinated graphical feedback. And that really opens up a kind of a large landscape of applications. So the big catch with a lot of these systems, these three systems here, is that it really, the utility of those techniques really hinged on the availability of surface area in the environment. So it's great while I'm sitting in front of this podium, be a great surface to check my email on, but if I walk, I'm not going to take this podium with me. I'm going to leave it behind. And when that happens, you kind of have to contract back to a small device again. And so when we were working on these projects, there was one surface that we kind of toyed with as an example, kind of fallback surface, kind of a last resort surface, and that was the human body. But we weshied away from using the human body because it's actually very tricky from a sensing perspective, right? It's curvy, it's soft, it's stretchy. We're always kind of moving and eating and growing. These are not typical dimensions you think of when you have when you think about an input device like a keyboard or mouse. Normally, you say, well, we're going to manufacture 100,000 touchscreens that are identical. We're going to upload the software, and voila, it works. But we know there's a lot of different models of human to contend with. People complain a lot about Android fragmentation, but there's 6.5 billion models of human to contend with, and that makes it actually very tricky from a sensing perspective. Another kind of big problem is that people are very sensitive about how their bodies are instrumented. So there's very few things that we currently wear on our bodies that aren't a fashion item of some sort, or at least making a statement of some sort. And so whether kind of wearable devices like Google Glass are going to be seen in the same light, really remains to be seen. It's a battle that still has to be fought. Now, I wear glasses, which is an assistive technology, and watches were able to achieve kind of mass popularity about a century ago. So we know that it can be achieved, but good design is really key. But overall, we should aim for technologies to be minimally invasive and kind of out of the way and hidden, because that's going to be more kind of in tune for practical adoption. And then finally is that input on the body can be really socially awkward. So this is me with scratch input, and this is me scratch inputting on my body, and it's really pretty strange. It may be that this is super high bandwidth. This is the touchscreen of the future. I'm writing emails at like 100 words per second. It doesn't matter because no one's going to use this. They're going to think you have some kind of skin disorder. So on top of the kind of sensing design challenges, you have to make interactions that are actually palatable to people to use. It doesn't matter how cool it is or how awesome it is. If people don't want to use it, it's kind of a failure. And so we have to take all three of these things in consideration. So, despite all those obstacles, using the body as an interactive surface really had some really interesting benefits, and so I kind of plowed into it more as part of my dissertation work. Now, obviously, the biggest benefit to the body is that it goes wherever we go, so that's great. It solves that problem. It also provides a good deal of surface area. So now my smartphone is about, the size of my hand, and if we think about just kind of the upper extremities, it's actually a good amount of surface area for interactive tasks. Also, very interestingly, is the body is the only kind of device that we get training with from birth. As soon as you're born, you're basically learning how to use this device in a very capable way. So the fact that we can close our eyes and touch our nose and clap behind our back, we take that for granted, but that's a remarkable feat. We can't do that if I put an iPad on this desk and I said, close your eyes and swipe to unlock. I could be there for 5 minutes. So it's actually a really interesting kind of perspective when you think about the body as a device that we have extreme training with. Also, when you think about kind of skin-on-skin interactions, like with a finger on your palm, is you're getting double the tactile feedback, which has also some interesting ramifications for accuracy. So in my opinion, actually, the skin makes sort of for the ultimate touchscreen in many respects. So because of all those reasons, I kind of honed in on the human body as a specialization of appropriated surfaces. And it's a very kind of unique and unusual domain. And it's a little crazy, I will admit, but that's why I liked it, and it's why I chose it for my dissertation work among the other topics that I work on. So when I first began researching in this area 5 years ago, on-body input and projection systems are really nascent. They're either conceptual or otherwise kind of extremely constrained. And so the real kind of fundamental question at the time was, is this even possible? Can we actually turn the body into something like a touchscreen, or at least a computing platform. And fortunately, there's a very large toolbox of techniques that we can draw upon and really more importantly adapt for use on the body. And actually the kind of core technical component of my dissertation was seeking out and kind of identifying opportunities in the sensing space that would actually allow this paradigm to be practical and successful. So first I want to talk about skinput, and this was really my first whole body kind of centric research project that looked at kind of using the body as a computing surface. And I got a lot of people thinking about the domain. One of the major takeaways from scratch input was the unique advantages of acoustic sensing. So foremost, we get excellent transmission of sound through solids like this table, but also through liquids, many times better than air. So this means not only your table's good, but actually also your own body. And this means you get better signal transmission, but also kind of more faithful signal preservation as well. And both of those turn out to be really key. Acoustics also allows you to instrument an area with sensing without directly instrumenting it. So I could put input on my hand, but I could actually sense it down here, or like up on my upper arm. And so it gets the electronics out of the way and less invasive. Another decision that we made very early on was actually to focus on taps on the body, so more like touchscreen interaction. We didn't want to have to do scratch input on the body. We wanted something that was more like a touchscreen to start off with. And what's really interesting about taps on the body is that, and especially taps on the limb, is that when you make that motor action, there's an acoustic sound that gets generated from that impact event. And it's different by different parts of the body that you tap on. So if you tap on a bone or a muscle or a finger, they actually sound fundamentally different. And then subsequently, things like joints and other morphological features attenuate that signal in a unique way, sufficiently so that you can actually acoustically fingerprint the location on the body. And that's what we do in skinput. So just very quickly, there's really two types of vibratory energy that we use in skinput for localization. The first are compressive waves. When you tap the skin, a wave actually travels inside of you, compressive waves. And bones respond to this kinetic energy by basically translating and rotating like a rigid body. And then this causes the soft tissues around them to basically send compressive waves back out along their entire length. And then, of course, a sensor on the surface can detect these waves again. Then there's a second form of mechanical energy, which is a little different. And these are actually surface ripples. I've tried my best here in PowerPoint to do that, but actually a video is going to be a lot easier. So here's me tapping my arm. And what we've done is we've really obliquely lit the scene. And if I slow this down about 14 times, you can actually see these ripples propagating outwards at very high speed over my arm. And you can imagine what's very interesting here is that on soft tissues, it's going to be way more prominent. And we all know that computer scientists are among the most muscular people on campus. But I'm sure it works for everyone. But if you tapped on your elbow, for example, where there's a lot less soft tissue, you're not going to see these ripples as prominently as on my biceps, for example. And it's actually those kind of acoustic differences that let skinput work. So to actually capture these signals, we took advantage of a very powerful physical effect, which is resonance. And what's great about building something with a very particular resonance is that it naturally amplifies energy in a very particular narrow band, and it suppresses out-of-band noise. And this turns out actually to be really important in the body because there's a lot of extraneous noise that we don't want to sense. You can imagine when you're walking or eating, there's all sorts of bioacoustic sounds that are being generated. And so what we did to do this is we made two arrays of these cantilevered piezo films. And what we did is we modified the mass at the end of each cantilever such that we could alter their resonant frequency. So they basically became sort of like a mechanical FFT. And we actually tried using microphones and accelerometers first because they have a nice linear response across a range of frequencies, but we just really, at the time, there was not enough dynamic range to really pull this off well, and this approach did work extremely well. So here's actually a close-up of those sensor arrays. So what I'm doing is I'm sweeping this speaker here from about 10 hertz to 100 hertz, and you'll see that at different frequencies, different sensors are basically vibrating. So here the big ones are going, and then as I get higher frequency, the little tiny ones will start rattling around, and so on. And basically we have just a bunch of these that are very highly tuned to particular frequencies of interest in the body. So here's actually what the two arrays were situated on, the different frequencies, and this was made as an armband. And what we did to this armband is we attached also pico projector to the armband, kind of cantilevered off the armband. Now it's important to note that, so this basically allowed us to project graphics down on the arm, but you have to hold up your arm to a predefined location if you wanted the graphics to land correctly on the arm. So automatic tracking is something I'm going to talk about in the next project. So here's actually what those bioacoustic signals from the 10 sensors look like. And you can very clearly see that I'm tapping my wrist and my midarm. You can see that they're radically different signals. And it turns out that actually frequency band ratios, basically pairs of these sensors, were the most powerful for classification. But in total, we use about 200 different features as part of our support vector machine classification. Now, because the signal is really heavily filtered, as you saw from that, we can actually just use a raw amplitude threshold to actually trigger for segmentation. It works very well. And then once the tap is triggered, we derive a bunch of features in both the kind of frequency and time domain, and then we push that into a support vector machine for classification. And when that classification result comes back, we can use that to fire an interactive event. So here, just again, is a very quick video of the system being trained. And what I'm doing here is I'm tapping each finger 5 times, which is a very small training set. But I'm tapping my middle finger 5 times, my ring finger 5 times. And at the end of this process, we can basically train the system live. So as soon as I'm done with pinky here, it's going to switch. So now it's loaded. And now I can do live classification by tapping onto any finger. So actually, the signal is sufficiently kind of differentiatable that just 5 training instances actually gives you a pretty high level of accuracy. And so what you can do is take that classifier and hook it up to something interactive. So in this case, this is a very early example. We basically made our hands buttons, and we could play a game of Tetris. OK, so evaluation is a critical component of my HCI research. Otherwise, you really don't know if any of these techniques works. And also, kind of really importantly, is that by doing an evaluation like I'm about to talk about, is it lets you find out where the technique both succeeds and fails. If your user study only yields a bunch of successes, you have no idea really where to push the technology next. You need to know both the floor and the ceiling. And so for SCIMPA, we ran a bunch of different studies, about a half dozen different location studies, and then a half dozen different supplemental studies looking at particular effects. And I'm going to share just a few of those right now. So one condition used the 5 fingers like the buttons, which you just saw. And the fingers are really nice because they're kind of discrete. We have names for them, for example. They're linearly ordered, and that's really great. But unfortunately, they're also pretty hard to sense, primarily because the anatomy is really similar for the fingers, as you might imagine. In this test, we placed the sensor just above the elbow, so about here. So when you tapped your finger like this, the signal actually had to travel about 40 centimeters across 4 different joints before our sensors could pick it up. So there's actually quite a bit of attenuation going on. And accuracy was about kind of 88%. So that means about 1 in 9 times you tapped and misclassified, which is not actually all that great. But what was really surprising was our segmentation accuracy. Pretty much every single time a user tapped on their skin, our system correctly segmented it. So when they tapped, it saw the tap, and it pulled that out. It may have got the classification wrong, but it found it nonetheless. And just as importantly is that false positive taps, someone slammed the door or they got out of their seat, it didn't see those either, which is a really kind of unique strong point about SCIMPA. Yeah?
How much would you say that lack of accuracy or lower than perfect was due to the distance versus the similarity? So like if you had put the sensor around the wrist, would it have done a lot better, or still have a problem with the similarity of the fingers?
Yeah, I mean, it's primarily, so if you move it up here, you do get a lot better, but actually here and here has already passed most of the joints in the hand that are actually attenuating this signal. So it's primarily an anatomy difference. Actually, I'll talk about I'm not going to talk about all the study results, but I'll show you one right now where we actually looked to see if we could model what the drop-off was across joints. So one of the ways we did that, and just let me explain this slide real quick, is if you go to more diverse locations, anatomically speaking, like in this example, is your accuracy jumps up quite a bit, to about 96%. But to kind of look at the effects like you're suggesting is we actually place the sensor in the exact same trial above and below the elbow to try to model what the acoustic drop-off was between the 2 points. We didn't do it for the wrist because, again, we really wanted to get the sensor as far away from the possible, and we thought the wrist was too invasive. And so here, what happens is you basically get a drop-off of about 7%. And you can break down that analysis again by looking at what are the when you look at the confusion matrix, what aspects of what out of the 5 positions, where are they dropping off? So yeah, we try to capture some of the richer details like that. Also, to kind of push our system sensing abilities, we put, and most particular on kind of spatial resolution, is we put 10 locations on the forearm alone. And this was really kind of to push it. I mean, the forearm is actually a pretty contiguous part of the body, so putting 10 on the forearm we knew was not going to do particularly well. And actually it ends up at about kind of 82% accuracy. But what we wanted to do post hoc was look at different ways of combining these into kind of patterns. And actually, a lot of them are pretty logical. So, kind of stripes across the arm, for example, where you have kind of 5 buttons along the length of the forearm, you kind of get up to about 88% accuracy, approaching kind of 90% accuracy for about 5 areas in general. Another kind of critical question is how well does this work while walking, right? This we know is going to generate a lot of bioacoustic kind of noise and energy in the system. How well is this going to work? And so to actually test this, we put 2 participants on a treadmill and actually had them train and test the system while both walking and jogging. And the results are actually reasonably promising. Amazingly enough, our segmentation accuracy was basically the same. So the true positive segmentation in both cases was 100%. So even while you're jogging, just the kind of very relatively subtle sound of a finger hitting the skin actually was detected every single time, which we thought was a really great result. And in the jogging condition, there was a few false positives as well, but overall it was pretty good. But you can see definitely that the kind of classification accuracy did take a hit. So the signal was definitely getting kind of muddied. So jumping to potential uses. So you can imagine clearly kind of like a music player strapped on the upper arm. Like you're out for a jog, and instead of having to reach over and kind of press these diminutive buttons, we may be able to just use our hand as kind of the interface, change the volume, pause the song, and so on. But I think it actually gets a lot more interesting when you couple this with projected graphics, because this starts to kind of approach interactions like you might do on a smartphone today. So what you're seeing here is actually kind of a button-based hierarchical menu. And the way we achieved this was actually by having the system learn what those 4 locations actually sounded like on the human body. We fingerprinted them. And then we can basically hook that up to an application like this. OK, so that's kind of an overview of Skimput. And the big success of this project was putting forward a novel technique for enabling touchscreen-like computing on the skin. It was really the first system that could achieve that in a plausible, kind of feasible, real-time manner. But and those were all big wins, but there was also some significant drawbacks. So clearly, while the accuracy was acceptable for a proof of concept system, clearly it's kind of lacking for practical adoption. And although it could detect touches, we couldn't do drags, and overall the kind of spatial resolution was fairly low. As I mentioned before, the projection was fixed, so you had to kind of hold your arm up to the same point, which is clearly not great. And also, and probably the most significant to kind of widespread use, is you had to train the system. A per-user training model had to be employed to get that accuracy. And we know that's going to be an obstacle. So a lot of these kind of limitations, but also the successes, fed into our motivation for the next system, which is Omni Touch. And this really, we feel like, addressed a lot of those shortcomings. So let me actually jump first to the video so you can compare across the 2 projects. So Omni Touch can appropriate the body just like Skimput, but also can appropriate other surfaces proximate to the user, so things like walls and tablets and newspapers and whatever. It's also multi-touch, and it's click and drag sensitive, and it has a spatial precision approaching that of a touchscreen, which I'll get to later. And really just very importantly, is that Omni Touch doesn't require any training. So I could take this system, and I could put it on one of you in the audience, and it work like you're seeing here in this video. Another kind of element that moved beyond Skimput was the ability to automatically identify and track surfaces. And it's independent of how they're oriented in position. So actually, the projector is not perpendicular to this notepad. It's actually at an angle, but we're basically folding it down before we project it such that it can land onto the surfaces correctly. It's not trapezoidal or otherwise distorted. And it tracks, and we've gotten the frame rate actually up quite a bit better. We can keep providing input to it, and so on. And what's cool is that if I held up my hand, which is a much smaller surface, it would automatically size it to fit my hand. So how does it work? Well, there's 2 really key components. Skimput was bioacoustically driven. Omni Touch is computer vision driven. You can see that there's a pico projector and a depth camera. And what you probably should be thinking, if you're a normal person, is I would never wear this. And you would not be alone in that opinion. I wouldn't wear it either. Even at CMU, it'd be pretty dorky. But importantly is we didn't really build it to be pretty. We really built it to explore interactions that weren't previously possible. And what's really exciting is that there's nothing fundamental preventing miniaturization. So actually, this is the first prototype, which is this really kind of crazy shoulder contraption. And within about a year, we had moved to this device that could clip onto a shoulder bag, basically. And really the kind of question you should be thinking about is, what is this going to look like in 2 or 5 or 10 or 20 years? How would you feel if this was projected, for example, from your smartphone or from your watch or from the sides of your laptop? Because that's actually where the technology is going to be very soon. OK, so let me quickly share some details of how the system actually operates. Here you can actually see the debug output on our hand. So you can see it can actually detect hover and click states, and it is multi-touch. And the way it does this is by taking the depth camera. So this is the same scene. What we do is we cull all the values that lie outside of basically 1 arm's length. So if you're basically more than 2 meters away, we're not interested because you can't manipulate it with your hands. And that actually discards a lot of background noise, as you might imagine. Then what we do is we compute a derivative of the depth map. And what we can do is scan over this image, looking for slices, pixels that are characteristic of fingers. And because we have distance information, because it's a depth map, we can actually convert pixel distances into real-world units, like millimeters. And this is really important because we have a lot of morphological data on fingers. We know how long and how big fingers should be and what the diameter of a typical finger is. And so what we do is we build a template, but it's actually an elastic template because there's not a paradigm kind of prototypical finger. We build an elastic template that's kind of probabilistic, and we look for fingers that meet those criteria. So here again is the depth map, but this time it's marked up with all those slices of fingers in blue. And so you can see there's, every now and again it'll pick up other things that are kind of finger-like, but you'll notice it's not picking up my wrist. My wrist is also kind of a big cylinder, but obviously it's too thick to be a finger match. So the kind of final step is to actually merge all of those slices into paths. And again, we know how long fingers are from a lot of anatomical data. So if it has the right thickness and the right length, we can basically merge that into a finger. And it ends up looking a lot kind of like a skeletal model. And it honors things like occlusion. So if I tuck in my fingers, obviously, they'll disappear to the system. And we have a kind of a similar set of computer vision techniques for detecting click and also for recognizing surfaces in the environment that are candidate for projecting on. So again, some quick highlights from the user study here. So the ultimate goal was obviously to turn everything in the world around us into a touchscreen. So the obvious question was, how close can we get to touchscreen-like accuracy? And the answer is actually reasonably close. So we looked at accuracy, spatial accuracy, in both clicking and dragging tasks. And this modeled both the error of the tracking approach and also the reprojection, because there's inaccuracies in both, and also the user error. So here you can actually see our drawing task, and it basically presented a bunch of 1D and 2D stimuli to users, and their job was to trace the path. And we could measure their deviation from the path, which was about 6 millimeters, which is pretty small. And then to evaluate click spatial precision, kind of more like a touchscreen, is we had participants click thousands of different crosshair trials. So something would light up in red, and they would click it on these 4 surfaces. And so we had the hand and the arm as examples of on-body interfaces, also as surfaces with more curvature. And then the pad is a handheld object, and the wall is kind of a large, static, fixed surface in the environment. And here's just kind of a quick peek at the results. So what we've done here is all the kind of gray little tiny circles here are all the click trials from all the participants. There's no per-user correction here. And they're rendered on top of our crosshairs. So everything here is in millimeters, and it matches the kind of real-world size, as you can see on my hand. And primarily, you're seeing these green ellipsoids. So these are 95% confidence ellipsoids. For each crosshair, they encompass 95% of the touches. And you can see they're relatively centered over their respective crosshairs, but nonetheless, especially kind of in the horizontal axis, there's a lot of overlap. So if you ended up in this region, it'd be hard to know if you wanted that crosshair or that crosshair. But if we look at the wall condition, this is actually, I think, much more indicative of where the technology is going. So here you can see that overlap is mostly gone. And that's because the wall was more stable and it was flat and so on. And this, I think, really illustrates where the technology is going. Because the depth camera that we built this on, if people have worked with Kinect-like depth cameras, was only 320 by 240. So that's 1/10 of a megapixel. So this is the kind of accuracy we were able to achieve with 1/10 of a megapixel. So the question is, as future depth cameras come out, as they did actually at CES just a few months ago, what kind of accuracy can we achieve with 1 megapixel or 5 megapixel cameras that we know inevitably are going to come? So actually, I think kind of the big result from this research was that we know that kind of interacting on the environment in a touchscreen-like fashion is actually already kind of done. It is almost a solved problem at this point. There's still a lot of work to be done to kind of improve the kind of fine accuracy, but overall, we know that it can be done, and that's actually really exciting. And actually, even though this project is now about 18 months old, nonetheless it's still regarded really as the most capable system to date in this space. Okay, so there's one more approach that I want to talk about quickly, and it has a really radically different flavor than the other two projects. Touche is actually electrical in nature, and more specifically, it's capacitive. So if you look at the construction of a typical touchscreen, it has really basically three basic layers. It has this neutral substrate, which is basically there for structure. It has a conductive layer, and then that's covered by an insulating layer. And if you look at how humans are built, it's actually quite coincidental. We're basically built the same way. We have our bones for structure, on which kind of our soft tissues hang, which are conductive, and we're covered by an insulating layer called the skin. And what this means is that we can actually turn the human body into a crude capacitive sensor. Now, the human body was never designed to be a capacitive sensor, so it actually makes a pretty poor one. But if we use a more advanced form of capacitive sensing, we can actually pull this off, and that's what we did in Touche. So before I get into that, let me give you a very kind of general overview of how capacitive sensing works. So most capacitive touchscreens inject a single AC frequency signal into that insulating layer. And what they do is they measure the single value. That's typically either a frequency shift or an amplitude shift. And what this basically does is when a user touches the screen, the value goes up, and if they let go, the value goes down, or something kind of equivalent to this operation. And what this means is that we can use basically, and most systems use, just a simple threshold for knowing if a user has touched or not touched. Now, this is a little bit more problematic on the human because we can't really control the form. And so it actually turns out to be a much kind of messier signal, and the threshold changes over time. And also, this lets you do touch and no touch. It's actually quite a bit harder to do things like gestures, right? So to do this, and this is with colleagues at Disney Research, is we looked at how a swept frequency AC signal could be used to get more information about touches. And what I mean by that is that instead of just measuring a single value like most capacitive sensors, is we actually sweep over a range of frequencies from about 1 kilohertz to 3.5 megahertz. And what happens now is that when a user touches, all of these values change, and in different ways, in kind of complex ways. And what Touche is actually measuring is the impedance of different pathways through the human's body to ground. And so what we get is not just a single impedance value or capacitive value like in the previous systems, we actually get a whole kind of continuous curve. And this turns out to be much more expressive than just touch or no touch. We can actually support quite rich interactions capacitively. So like Omni Touch, Touche allows us to appropriate a lot of different things in the environment. So for example, this is a doorknob that I picked up at Home Depot. There's nothing special about it other than I've attached a single wire to it. And we can recognize now a series of gestures, about 5 gestures capacitively. And we can do the same thing similarly on the human body. So this, instead of using the earth as ground, we've actually have 2 electrodes here on either wrist. You can't see it, it's cut off. And basically we're measuring the capacitance between 2 points in the human body, or really the kind of impedance. And this offers a bunch of different gestures. So for example, you can even capacitively sense through your head, or different hand grasps. And this could control something like a music player, for example. Okay, so that kind of gives you an overview of these 3 techniques that we were able to develop as part of my kind of the core technical component of my dissertation work. And what these systems really did was answer that fundamental question that I asked earlier, which is, is it possible to actually appropriate the human body for interactive use? And I think these systems, largely answer that question, which is yes, we can. And that actually was a non-trivial, that was not an obvious answer when we started this research 5 years ago. Now, of course, there's much more work to be done on the technical side, as always, and I look forward to kind of keep advancing that work in my future research. And what's nice is that in the past couple of years, we've actually had kind of the titans of industry start to join this effort. So I saw this come out a few weeks ago. This is kind of a Google patent that shows, hey, what happens if we have laser projection on the skin, and what kind of interaction techniques we can bring to bear on a platform like this. So it's really exciting that other kind of researchers are coming into this domain with enthusiasm and extending the work. Okay, so with the kind of question, the fundamental question of whether or not this is possible behind us, this actually really kind of opens up a lot of other questions. There's a lot of other things to consider if we're really going to make this feasible. If we can make it feasible, what do we do with it? How do we design it? How do we amplify human abilities, if I go back to my original question? And these are really the types of questions that move us towards informing the design of future systems. And this is really what I'm working on now and in my future work. So I have a lot more questions than I have answers at this point, but I want to show you some projects that are laying the foundations of research that I am pursuing now beyond my core technical work. So a critical class of question is where? Obviously the body is not like a laptop where there's a clearly defined screen. There's lots of options for where interfaces could appear on the body. So, for example, where is there sufficient surface area? Is curvature going to be an issue? Where would it be comfortable to touch? Would you ever lend your arm to a stranger to make a phone call? Who's going to be okay with that? So there's a lot of kind of questions in this very similar vein. So one very important question to ask is, where would it be appropriate to even project these touch-based interfaces on the body? So clearly not all places are created equal. And this is really kind of a big multifaceted question that we're just digging into. But to get some initial bearings, we just wrapped up this 2,000 participant mechanical Turk study, and then also to produce a bunch of heat maps, which I'll show you on the next slide. And then we complemented this model with a bunch of expert interviews of people that deal with the human body as part of their work. So things like massage therapists and chiropractors and dance instructors, people that know about aesthetics like tattoo artists and motion and touch. And they basically compiled into these models that we're working on now. So here's a quick look at what that data sort of looks like from the crowdsourced component. And you can see that there's some obvious places you don't want to go, but overall, your hands, especially below the elbow, are actually very valid targets, and people are pretty comfortable. And what you can do is you can actually start asking questions that span different poses. So a lot of the previous on-body work has really been hand and arm-centric. But there's actually some really interesting possibilities. It's hard to see on this projector, but your legs actually become quite valid places for interaction in certain poses. And then we can also start doing things like pulling apart these heat maps by gender, and also by touching interfaces versus looking at interfaces. And you can also say, is this you touching, or is this someone else touching, a stranger or a friend? And so you get a lot of kind of interesting data. And then, just very quickly, here actually, so we made our experts do these kind of silhouette exercises, sort of like we did for our crowdsourced components, and had them think aloud. And there was a lot of interesting commentary about the aesthetics and also gender differences that we're basically starting to put together and compile now. So another really critical question is how often people see different parts of their body. If we're going to have visual information be the primary modality, how often do people even see different parts of their body such that we could use it as a kind of a projected surface? So it's really important to understand, kind of both the reaction time but also the distraction characteristics of visual information on the body. And so to kind of dig into this, we built these little devices, which are really nothing more than an LED and a button. And they did one thing. They would sleep for a random length of time, start blinking. The user would notice it at some point, press the button. It would save how long it took, and then it'd go back into sleep until it started blinking again later on. And we just basically attached these to people for hours and hours when they did their daily routines, and we could model how often they saw different parts of their bodies. We did a bunch of different places here. And you get back some really interesting data. So one way to visualize that is there's this cumulative probability diagram. And what we can do is ask questions like, what's the probability of a user reacting to a visual alert on their wrist within 5 seconds? And basically we can use like a lookup table and say, oh, well, it'd take us about, it'd be about a 50% probability of responding within 5 seconds. If we wanted a 90% probability, we'd have to wait about 50 seconds in this case. And then if we look at a totally different location like the waist, you can see it actually be several minutes before we could really get a 90% chance of the user reacting. So kind of armed with this sort of information, we can much better match the alert priority to different body locations. And you kind of strike a balance between interruptibility and also getting the user's attention in a timely manner. Okay, so there's a lot of questions surrounding where, and I showed you just 2 quick examples. But that's really just scratching the surface. There's also a lot of what questions. So, what should on-body interfaces look like? What applications are really well suited for the body? We know that these have had very successful applications. What are those for the body? Is there an ideal widget set for the body? Are we going to really be using, drop-down menus and scroll bars on our hands, or is there a totally different way to think about it? So, one question we should be asking is, are there modalities beyond direct manipulation touch, kind of poking fingers at things? And in Omni Touch and Skinput, we mostly did that. We kind of borrowed a successful paradigm and brought it onto the body. And that was a good place to start. But, these interfaces are really 2D and rectilinear, and we know that our bodies are neither. So it's clearly, we got to start thinking about this. And, one of the real dangers is basically just shrinking interfaces down and sticking them on the body, right? This is sort of what early mobile UIs did. So if you've ever used Windows CE, you know what I'm talking about. You don't just shrink things down and kind of pack it into a small screen. You have to think a little bit more holistically about the design, and the body is going to be no different. And we know that mobile and desktop UI, layout, and widget sets have been the product of decades of evolution. Are we going to need to develop new principles for the body? So another question that I just brought up is, what are the kind of other modalities exist beyond kind of fingers clicking buttons? And actually on the body, we have some very interesting degrees of freedom. So for example, we can flip our hands, which is not something we can do on a typical mobile device. And we can also leverage gesture and position simultaneously. And with coordinated graphical feedback, there's actually some really rich possibilities that exist, where if you're just gesturing in free space, it's actually you get lost very easily. And then we can also really start thinking about some interesting synergistic uses of the body. So for example, we can use our hands like a book. So instead of having to scroll, we can actually instantiate a book metaphor. And we could swap between lots of different metaphors very fluidly on the body, and interfaces will have to adapt to these different kind of changing circumstances. So this is really just the start, I think, of a really kind of broad area. And I think the fact that there's so many diverse questions to ask is actually testament to the novelty of the field and really the diverse set of methodologies and tools that we have to really bring to bear for this kind of new space. And so there's a lot more work to be done on the on-body area, certainly. And I look forward to pushing that forward along with my other threads of research, which I didn't get to talk about today, but primarily in haptics and user interface design and also augmenting touch. So that just brings me to my very high-level contributions of my work and also the conclusion of my talk. So most immediate is that I develop novel sensing approaches and interaction techniques with an applied human-centered focus. So in this talk specifically, I talked about Skimput, Omni Touch, and Touche. And these were really significant contributions technically. They expanded the envelope of interactions and also put new tools into the toolbox of techniques that researchers and practitioners could draw upon. Simultaneously, a lot of the research outcomes have implications for today's devices, so we can make them better, often with kind of little or no modification. And third is that I often use, or really more appropriately repurpose, technologies that are available today to kind of envision the future. And this is, I think, an approach that's shared by many of you in this room. The result for me is often some kind of hideous prototype that's duct taped and glued together, or a depth camera on the ceiling, but nonetheless it kind of lets you look forward and imagine what could be, and more specifically, what that should be and what it can be. It also lets you see where the challenges lie, right, and also what the potential benefits might be, and that really informs the design of future systems and also research directions. And then finally, at kind of a very high level, is that human-centric innovation and research around it really can produce concepts, modalities, and technologies that have the possibility to inspire entirely novel forms of computing, which is obviously very exciting. So we know that there's something beyond the mouse, there's something beyond multi-touch, and there's a lot of people kind of probing the barely possible of today to figure out what that might be, and that's a very exciting place to operate in. So on that note, thank you, and I would love to take questions.